When an original length L sub 0 of a material is heated up so that its temperature changes by delta T, where delta T is a relatively small value, so that the expansion with temperature is at a relatively constant rate, then we're going to say that the change of length is the coefficient of thermal expansion multiplied by the length times delta T. This coefficient is nothing but a proportion. If we multiply L naught by, well, let's think of multiplying alpha by delta T. Alpha delta T tells us the proportion by which the length L naught changes. The delta L is then alpha delta T times L naught. And alpha is the number that we multiply by delta T to get the proportional change. So we say that alpha is proportional to the length change per degree. It's a proportion of length change per degree. If we have a rectangular region, length L by width W, of a material with coefficient of linear expansion alpha, this is called the coefficient of linear expansion, as you should know by reading. If the coefficient is alpha, then alpha delta T again is the proportion by which lengths change. Now by length we mean any linear dimension of the material. So that for small alpha delta T, and alpha delta T is almost always small, if we start with length L, we're going to end up with length L plus alpha L delta T. And if we start with width W, we're going to end up with width W plus alpha W delta T. In that case, let's ask the question, what happens to the area of this thing? Again, remembering that alpha delta T is a small proportion of the original length or width. Okay, what we get is the area A2, which is the area after we've expanded, is going to be this length L plus alpha L delta T times the width W plus alpha W delta T. So we have this expression for the area A2. If we multiply this expression out, we see that our area A2 is just LW plus 2 alpha LW delta T plus alpha squared LW delta T squared. Now, one thing that's important here is that alpha delta T is pretty small. So that alpha squared delta T squared is going to be really small compared to anything else in this area expression, and we can therefore ignore it. And we can simply say that the area A2 is pretty close to LW plus 2 alpha LW delta T. Okay, so we're going to say that A2 equals A1 plus 2 alpha 1 delta T. Now, what do we mean by A1? Should have mentioned that over here, but A1 is just LW, the area of the original figure. And we see that we got LW or A1 here, and we got LW or A1 here. We simply write this expression substituting A1 for LW, and we see that area 2 is A1 plus 2 alpha A1 delta T. This says that the area increases by the proportion to alpha delta T. Now, this coefficient 2 alpha, we're going to call it beta. Okay, the coefficient of area expansion. And we can say that A2 is the original area plus the beta delta T times A1, where beta delta T is the proportion of area increase. If we did a similar thing for a volume, a length times a width times a depth, or whatever, okay, a length, a width, and a depth going back in this direction someplace, everything would come out pretty much the same. We would end up with as we end up here with an area change of beta times A delta T, okay, where beta delta T is the proportion, and beta is equal to 2 alpha. For volume, we would end up with a 3 alpha delta T proportion of volume change. So that for linear change, we have just an alpha delta T. For area change, we have a 2 alpha delta T or a beta delta T. For volume change, we have a 3 alpha delta T. The 3 alpha is sometimes called gamma. It's often just left 3 alpha. And that gives us our proportion of volume change. If we go back to a linear object like a wire or a beam or something that's fixed, say, at both ends, then if we change its temperature, it's going to undergo a thermal stress. Remember, stress is force divided by cross-sectional area. The force divided by the cross-sectional area is called the stress, and it's proportional to the strain. What's the strain? The strain is the difference in the length, the difference in the proportional length of the object, which turns out to be just alpha delta T. And of course, the ratio of stress over strain is capital Y, which we call Young's modulus. Okay, Y is F over A, the stress, divided by delta L over L naught, the strain. Delta L over L naught, as we see from the definition of the coefficient of expansion, is just alpha delta T, and that's where we get this formula for thermal stress.